Okay, today we're going to cover Chapter 29, Sections 9 through 10, and we just have a few problems to practice with. So, starting with concept question 11, we have a wire loop, current loop, okay, and current is flowing out at the top, in at the top, that's the X, so it's in at the top and out at the bottom. Okay. This is a cross section, so we're looking at it on the side. And then we have a bar magnet that is to the right of it with the south pole nearest the wire loop. Question is there an attraction between them, a repulsion between them, or no force at all between them? Okay, the main idea is that this current loop acts like a bar magnet, acts like a small north and south pole based on its dipole moment. So the question is, well, what is the direction of its north and south? Where is its north and south, or where is its dipole moment? And that is determined by the direction of the magnetic field it creates along its axis, which we can find by our right-hand rule where we curl our fingers. So it's curling in at the top. Okay, so if I were to put my hand around the loop, so imagine the loop. I've got my hand curling around the loop. It's going in at the top, curl out at the bottom. My thumb points to the left. So along its axis, the magnetic field points that way, and that's the same direction as its dipole moment, which is a representation of its north and south pole, pointing from the south to the north. Okay? And so, if that's the case, then I know that if I had just another bar magnet here with its north and south pole oriented this way, this would be a repulsive force. South poles repel each other. And so this bar magnet would repel this wire loop. Okay? All right, so that would be a repulsive force, F this way and F this way on that one. Okay, now number 12. Describe in detail with words and pictures how a permanent magnet can pick up a piece of non-magnetized iron. Okay, this is a good problem to really think about what is going on. You've done it all the time, a little fridge magnet, pick up a paper clip, we do it all the time. How does that work? Okay, so here is a bar magnet, and I'll just put north and south that way. Okay, and I'm going to have a piece of material here, and this will be my paper clip, and it's initially those are far away, and so when that happens, the dipole moments of all the molecules are randomly aligned. They're just all over the place. Okay, that's an unmagnetized piece of iron. All of its dipole moments are all over the place. When you bring that closer, okay, then these all align with the field this creates. Now this creates a field kind of down. Okay, so this, I'm going to draw dotted lines coming out of the North Pole into the South Pole. Okay, so all these are going to start to align with it. And since each of those are a dipole moment that create a north and south pole, their dipole moment pointing from south to north, this now has an overall south side and an overall north side, which makes it like a bar magnet, and it can be attracted now to this bar magnet. Okay. And now if we had reversed this, put north here and south here, same thing would happen. These would have all just aligned the other way, and with the south pole on the bottom of the bar magnet, all these would have pointed towards it, which means their north pole's on the top, and they would still be attracted. So all the molecules inside a material, a magnetizable material, have little dipole moments, and they can align with magnetic fields and therefore become little magnets. Okay, let's take a look at 38. Go look at that problem and see what you can do with it. Okay, so we have a rectangular loop of wire. I'm looking at it on its side. We know its length. We know the current flowing through it, 0.5 amp. We know the length of each side, L. And we know the magnetic field it's in. And that we know that the axis of the loop perpendicular to its plane, so that would be this direction. So here's the plane of the loop. The axis perpendicular to that is 30 degrees away from the field direction. So I'm going to draw a field like this, and that will be the theta that I know. So this is B, and I know theta. So we know theta, we know the B field, and we know the length of that wire loop, and we know the current. The question is, what is the size of the torque? Okay. Well, we've analyzed this thoroughly in a previous video, and we now know that the torque on a loop is equal to mu cross B, which is mu B sine of theta. And mu is I times A, which in this case is L squared, because it's a square loop, so I can find it from the length. It's just side length times width. B sine of theta. Okay? And the direction would be so that the mu aligns with B. So the question I have is this theta that theta? This theta is supposed to be the angle between mu and B. Does mu point this way? And the answer is, yeah, it could, or it could be pointing the other way. Okay, it's always normal to the plane of the loop, and its direction is given by the right-hand rule. So if it was pointing this way, okay, then in that case, that means current's flowing out here and in here. So out, down, and in, and then up along the back. Okay, and so if we curled our hands in that direction, like this, okay, then our thumb would point in the direction of mu. Now, if it was going the other way, which we're not told, we'd get the same numeric answer. It would just curl the other way. The torque would be the other direction. And since it doesn't only ask for magnitude, then this is sufficient. Okay, so plugging in all our numbers, we're going to find the torque is going to be equal to 7.5 times 10 to the negative 4 Newton meters. That's the correct unit for torque. Okay, so that'll be our answer. Again, the important thing is recognizing what is mu, how does it relate to B, and how's the angle between them. So this is our fundamental relationship, and then we have to recognize what the values mean physically. All right, then our final problem for today is our short lecture today, 73. Okay. Now this one could be an easy problem, but I want to focus on the process of analyzing. So this one is a good example of applying multiple ideas. Here we have a wire loop. We have a wire loop, and the current is flowing this way in the loop, which means at the top of this square loop it's flowing into the page, and at the bottom of the square loop it's flowing out of the page. Okay, and the magnetic field everywhere is uniform and points this way. So it's same size and all horizontal. All right, so our question is how big of a magnetic field does this need to be to hold this up at 25 degrees, an angle theta? We know the mass of this. We know the size of the current flowing through it. We know the side length of it. And we know this theta. So our question is what size magnetic field will hold it up? Okay. Now, just as a clarifier, up means vertically up. Okay, this is vertical, okay, which means gravity points straight down. Okay, gravity points downward. Okay, so think about how you're going to use those ideas to solve this. Okay, the thing that I hope jumped to your mind is that this is a torque problem. In fact, it's Newton's second law for rotation, where if it's resting there at this angle, then the net torque must sum to zero, and we have two sources of torque. We have the magnetic torque trying to make this thing spin, and then we have the gravitational torque trying to pull it back down. Okay, so looking at it, I'm going to redraw it here. We have it's a square loop, and as we saw in our derivation, there's no force on the wires that go this way. It's just the ones that cross the magnetic field this way. Okay, and so since this one is our pivot point, I'm going to basically rederive that, and we'll see that we could have chosen a pivot point here and got the same answer. Okay, but we'll go ahead and choose this as our pivot point. So the main idea is that the torque about that point, call it A, is zero. It's not moving. That means it's not accelerating. So it's zero. So let's go ahead and choose a positive and negative. I'm going to choose counterclockwise to be positive. And let's plug in what are our torques. Well, is there a torque? Is there a magnetic force on this wire? Yes, there is. And just like we saw in the derivation in the video and in the text, there is. But the distance to that force is zero because that's my reference point. So the force on this point doesn't cause a torque about that point. The question is, well, is there a torque of the force on this point? We do know there is. We do know there is. It's in fact straight upward. This would be FB. And the R vector would be from A to where the force is applied, which is of length L. So our R cross F would be L. That's the length. F, you can just put FB, and then sine of the angle they make. So that's the angle that they make, which, need to be careful, is not this angle. Okay, so I'm going to focus this right here. We've got our R and our force. Okay, this is our F sub B. And this is the angle I need to plug in to my sine of the angle between them. Okay, so I'm going to call that theta 1. I need theta 1. Okay, but this is the theta I know. I'll call it theta 0. But if I recognize that's measuring from the horizontal up to the loop, so that's this one right here. And I know that by a trig identity, well, this is basically theta 1 is 90 minus this one, since this force is straight up and this reference is straight horizontal. Then this is 90 minus. Okay. And that's the same thing as cosine. Same thing as cosine. Okay, so we dealt with the torque. I kind of got ahead of myself dealing with just this one, but that's not the net torque. That's just the magnetic torque. It's positive because I've chosen that way to be positive. Now we need to subtract the torque due to the gravitational force. The gravity acts on the center of mass and points straight down, Fg. Okay, so the distance from the pivot to where that force is half L. The size of the force is mg. And then the angle they make, okay, so I'm going to zoom in here. R points like that again. G points straight down. That is the angle they make. I'm going to call that theta 2. This would be sine of theta 2. All right. Now, if I go like this, I know that that is theta 0, which is the number I'm given. And so theta 2 is 90 plus theta 0. So this is going to be over 2 mg sine of 90 plus theta 0. Okay. All right, and so something I know about the trig identities is that's also cosine of theta. This is minus L over 2 mg cosine of theta 0. So that's just identities. Sine of 90 minus or plus theta is the same thing as cosine of that value. Okay, so with that in mind, remember all this equals 0. That's all my net torque, so this equals 0, which means I can cancel out an L. I can cancel out the cosine of theta. And now I can write FB equals L, cancel that out, mg over 2. And I just now need to remember what FB is. It's the magnetic force on that wire. So that wire, remember this is a square. It's length this way and then length into the page. And they are perpendicular. So this is just going to be the force is, it's I L B equals mg over 2. And so B is then equal to mg over 2IL. And I know all that, so I can plug in my numbers and I'll get 0.16 Tesla. That is the magnetic field, which is a sizable magnetic field to hold this up. Now I wanted to point out some values here. In the problem, this is a large rectangle. It's a 2.5 meter square square, okay? And it weighs 2 kilograms. That's a pretty big rectangle. It must be pretty small wires to only weigh 2 kilograms. Okay? But that gives a sufficient amount of force along that 2.5 meter long length there to be able to lift it up this much. Now what's cool is it actually doesn't matter what angle. It doesn't matter what angle. Because of this geometry, because of how the gravitational torque acts on the center of mass and how the magnetic torque acts on the top wire, it could be stable at any angle. It would work because the angle canceled out. Now if I increased the magnetic field, it would have a greater force this way, which would lift it up, but then the gravitational force is pulled back down at an equal amount.